Hello and welcome to the next of the lectures under this course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered under the NPTEL platform. In the previous lectures of this week, we have seen how operations on fuzzy sets can be seen as performing operations on the 0-1 interval. We have seen that there are different possible interpretations of the operation themselves, and we were left wondering on how to choose a particular operation. Towards this end, we have made a beginning by looking at a partial order relation that could be defined on the set of fuzzy sets, thus making the set of fuzzy sets a poset. In this lecture, we will look at a special type of poset called lattices and go on to show actually we could have a lattice structure on the set of fuzzy sets. Recall that when we discussed that operations on fuzzy sets can be seen as operations on the unit interval 0-1, we had many interpretations for the fuzzy conjunction. Given these two fuzzy sets A and B, as denoted by the red and blue curves, we saw that if we were to use the min operation, then the fuzzy set that we obtain is given in black. If we used the product operation, we would get the fuzzy set as in magenta. Or if we did use the third operation, which later on we will see has been proposed by Ukashevich, we would get the conjunction of these two fuzzy sets to be the curve as given in magenta curve. We have seen that as the operations change, so do the shapes of the curve. As an important outcome of this, we have seen that it is possible to generalize this. These operations can be generalized by extracting the properties that we want them to hold. In that sense, it was a very positive outcome. However, we are still left wondering, given these many operations or interpretations of conjunction, how should one choose these operations? Is there something special about each one of them? We hope that by the end of this lecture, you would get some partial answers at least for this query. Let's quickly recall what a poset is. We have P to be a non-empty subset, non-empty set, and a binary relation denoted by the symbol less than or equal to. We say this tuple P along with the binary relation is a poset if this binary relation turns out to be an order relation on P. That is, it is reflexive, antisymmetric, and transitive. And we know that typically if the set P is finite, towards easier understanding and towards a way of graphically illustrating it, we take recourse to Hasse diagrams. We have also seen that a poset can be a chain, that means totally or linearly ordered. We say a poset is a chain if any two elements are relatable under that relation, the ordering relation. We have also seen a poset can be bounded above, bounded below, and perhaps both bounded above and below, in which case we say it is bounded. In this lecture, let's touch upon lattices. We could look at lattices from two different perspectives, an order theoretic or an algebraic perspective. In this lecture, we'll confine ourselves to looking at lattices from an order theoretic perspective. We will take up an algebraic perspective of lattices in the next lecture. We need to set the stage to discuss what lattices are, how they become special types of posets. Towards this end, let us introduce a few concepts. Let us consider a subset S of P where P is a poset. We introduce the notion of a upper set. So given a subset S of P, we denote the upper set of S by SU. This consists of all the upper bounds of the set S. That means all those x elements of P such that x is greater than or equal to s for every s. It's bigger than every s in S. Let us consider this now familiar set with different possible orderings. So essentially on the same set we have three different orderings, and hence we can consider them as three different posets. Let us now take the first poset. If we consider the set S to be P, A, then SU is set of all x in P such that x is both greater than P and x is greater than A. Now from the poset we see that this is actually the set, the singleton set 1. Now recall, the way to read a poset is like this. We see that it is a graph. The vertices are its elements, and if two elements are connected by an edge, then they are relatable under the order. And as we move from the bottom to the top, it is in increasing order. That means we read it as 0 is less than or equal to P, P is less than or equal to Q, and so on. While there may not be an edge between P and 1, by transitivity we know that P and 1 are also related, and that P is actually less than or equal to 1. So if we consider the set PA, which is a subset of P, with respect to the first poset, that is with respect to the first partial order on the set P, we see that the set of all upper bounds of this set S is nothing but just the singleton 1. Now if we consider the same set, under the second ordering, we would get a different set of superset, upper bounds. So now we are looking at P with the second order. We see here Q is an upper bound for P, both P and A. So Q comes into picture, and so is 1. 1 is an upper bound for P, it's also an upper bound for A. That is, it is bigger than both P and A. So SU will consist of Q and 1. On the other hand, if you consider the third poset, that means let's take P with the third ordering, and for the same S that we have considered, PA, the set with PA, if we consider the set of all its upper bounds, we see that P and A both are smaller than Q, so Q will be here. P and A both are smaller than B, so B also will be here. And of course 1 we know is the top element, is the upper bound for the entire set, so obviously 1 also will come here. So you see here that when we consider the same subset S, depending on the ordering, the upper set of S varies. Similarly, we can talk about the lower set of S. This is nothing but set of all lower bounds of the given set S. So if we consider the same set S, then we could also write the corresponding. We see here for the first poset, the only lower bound of P and A is the set 0. In this case of second poset, once again the only lower bound for both P and A is 0. Now let's consider the third order. So we have P and A. Once again, the lower bound for P and A is just the set with 0. However, if we consider S to be the set QB, and let's consider P to be the third poset, that is Q and B, and if we consider this as the subset S, and we want to consider the lower set of S, we see that for Q and B, P is smaller than both of them, A is smaller than both of them, and 0 is smaller than both P and A, which means by transitivity 0 is also smaller than both Q and P. So that means SL in this case would look like P, A and 0. It is clear now then that given any subset S of P, we can find the set of upper bounds and the set of the lower bounds, which are called the upper set and lower set of S respectively. Let's move on to the concept of least upper bound of a subset S. An element X from P is said to be the least upper bound of S if, firstly, X should be an upper bound of S, and it should be the least upper bound of all the upper bounds of S. That means it should be smaller than every other upper bound of S with respect to the ordering that we are considering. For instance, once again, let us consider the same three posets that we have. We have seen that SU, in the case of the very first poset that we considered, it has only one element, so this turns out to be also its least upper bound. In the case of the second poset, we know that both Q and 1, they are the upper bounds of the set P, A. Now the least upper bound is that upper bound which is smaller than every other upper bound. Clearly, that means Q is the least upper bound. Now let's go to the third poset. Here we saw that for the set PA, we have three upper bounds, those of Q, B and 1. However, we see that Q, while it is smaller than 1, it is not smaller than B. Similarly, B, while it is smaller than 1, it is not smaller than Q. Which means this set does not have a least upper bound. So what it means is, with respect to the third ordering, the set S consisting of P and A does not have a least upper bound. This is not to say that no subset S of P will have a least upper bound. Let's look at the set S with P and Q. Now if you look at SU, the set of all upper bounds of P, Q, you will see from here that one definitely is bigger than both P and Q, but by the definition here, you will see that Q is less than or equal to itself and Q is bigger than P. So the set of all upper bounds of SU of S would be 1, Q. Now, among these, if you are choosing the least of them, clearly the least upper bound of S is going to be Q. But similarly, we can talk about the concept of a greatest lower bound. By definition, it is a lower bound of the set S, and among the lower bounds, it is the largest of them, the biggest of them. Once again, let's look at the same three posets. We have seen that if we consider S as P, A, then SL with respect to the first ordering is actually only 0. SL with respect to the second ordering is also 0, and so is the case with the third order. However, we actually consider the set Q, B. Now, once again, if we consider the third poset and consider the lower set of the third poset, we know that we obtain P is smaller than both Q and B. A is smaller than both Q and B. So, 0. So, we get this set as the set of lower bounds of S with respect to third order. Now, to find the greatest lower bound means to give an ordering on these three elements. Clearly, 0 is smaller than both P and A. However, neither is P smaller than A nor is A smaller than P. That means we are not able to find a single unique element which is smaller than all of these lower bounds, which is greater than all of these lower bounds. Thus, in this case, we do not have a greatest lower bound for this set Q, Now let's come to the concept of supremum and infimum. These are nothing but the greatest lower bound and the least upper bound repackaged as these in terms of these terminologies. So given a pair of elements x, y, the supremum of x, y is nothing but the least upper bound of x, y. Typically, it is denoted by this symbol which we call the join. So when it is read as x join y, when we say x join y, we understand it as supremum of xy. Now if you have a set S, then the supremum of S is nothing but the least upper bound of S. It is also denoted like this, and it is simply read as join of S. So if we consider the same posets, we know that we have actually considered, so if we consider the set S is equal to PA, and we have found out the supremum of the set PA with respect to the ordering 1, the least upper bound is 1, so this is essentially the supremum. Thus, you could also write 1 is P or P with respect to the ordering 1. So similarly, we see that for other posets also, we can find this. Similarly, as supremum, we could also define the infimum of a subset S of P. If you have a pair of elements, the infimum of this pair of elements xy is nothing but the greatest lower bound of the set consisting of x and y. We will also denote this by the wedge symbol and read it as x meet y. If you have a subset S of P, the infimum of this S is nothing but the greatest lower bound of S, and it will be denoted as meet of S. Once again, we could calculate the infimum of any subset of S with respect to any of the ordering that we have defined on P. Well, in a nutshell, this is what we have. Given a pair of elements or a subset S of P, we can define and determine its least upper bound or greatest lower bound if they do exist. Let's look at some examples. Consider the set P to be the unit interval 0, 1 with the usual order. If we consider the subset S, which is, let's take this to be the open interval 0 to 0.5, and we ask the question, what is its infimum and what is its supremum? That is, what is meet S and what is join S? It is clear that 0 is the only lower bound. However, it does not belong to this. Still, the infimum of S is 0 and the supremum of S is actually equal to 0.5. Please note here, in the definition of the infimum or the greatest lower bound, the y need not belong to S. It is an element coming from P. Hence, zero or 0.5, even though they do not belong to the set S, they still can serve as the infimum and supremum of S. Let's slightly tweak this interval. Let's push 0 inside the set and consider the close to 0 open 0.5 interval. Once again, the infimum of S remains to be 0 and the supremum of S remains to be 0.5. This would be the same if you alter the interval S dually, that is, push 0.5 inside the interval and still keep 0 outside. The infimum of S will remain as 0 and the supremum of S will be 0.5. In fact, if the infimum of the set S belongs to S, that is when we call that infimum to be the minimum of S. Similarly, if the join S, the supremum of S belongs to S, then we say the join of S is actually the maximum of S. Let's finally consider this particular interval. So this is an union of two disjoint intervals, 0 to 0.4 where 0.4 is not included and 0.6 to 1 where 0.6 is not included. It is now clear then that if you look at the infimum of this set S is again 0 and the supremum of this set S is actually 1. You might recall from the previous lecture when we discussed the alpha cut based ordering of fuzzy sets defined by R, we have seen these two fuzzy sets. which are given in red and blue curves. And we have seen that for a particular alpha, the alpha cut looks like this. So for a particular alpha, the alpha cut for this fuzzy set A1 is union of these two intervals, and for the same alpha, the alpha cut of the blue curve, the second fuzzy set, is given by the union of these two disjoint intervals. We will see that even though these two intervals are different, the infimum of these two intervals is essentially the same, the left endpoints of the interval, and the supremum of these two intervals is the right endpoint of these two intervals, which are identical. Please recall the alpha cut based ordering of fuzzy sets that are defined over the real line. We say that two fuzzy sets A1 and A2 are ordered under this relation if these two inequalities are held. Clearly, if we consider A1 and A2 as the fuzzy sets, we see that for every alpha, even though we have only denoted for illustrated for one particular alpha, for every alpha we will see that while for some alphas the alpha cuts themselves may differ, the actual these two inequalities will still be held. In fact, the infimum of A1 alpha will be equal to infimum of A2 alpha for every alpha here, and similarly the supremum of A1 alpha will be equal to the supremum of A2 alpha for every alpha coming from 0, 1, beta, which means both these fuzzy sets are orderable with respect to this relation. In fact, we get A1 is less than or equal to A2 and A2 is less than or equal to A1. However, we have seen that these two fuzzy sets are not equal, and hence this relation does not satisfy antisymmetry, and hence we have seen that if we only consider arbitrary fuzzy sets, the set of all fuzzy sets on R, then with respect to this relation it does not become an ordered relation. We do not get a partially ordered set. So this is something that we have seen earlier, but perhaps now, after having discussed the concepts of infimum and supremum, perhaps now this will make more sense to you. Now we are in a position to discuss lattices, which are special types of posets. Let P be a poset. We call it a lattice if for every pair of elements the supremum exists. Similarly, for every pair of elements the infimum also exists. That is, for every pair of elements both the infimum and the supremum exist. In fact, it can be proven that it is sufficient for one of them to exist, and by the principle of duality the other one will also exist. However, for sake of completeness, let's have this as the definition. That means for every pair of points we want both the supremum and the infimum to exist. Towards amplifying this and emphasizing the relationship between the supremum and infimum and their existence, we actually indicate a lattice not just only with the set and the order relation, but also with the meet and join operations. Let's look at the posets that we have been discussing so far. It must be clear to us that the first and the second posets, all of them turn out to be lattices, because for any two elements, any pair of elements, you will be able to find the infimum and the supremum. However, the last poset is not a lattice. To see this, consider the pair of elements P, A. We want to see what is its least upper bound. So let's find out for this set S the upper set. And we have seen the upper set consists of Q, V and 1. However, while the set of upper bounds is actually the set with Q, V and 1, we are not in a position to find the least upper bound as we have seen earlier. So the LUV of P, A does not exist. Remember, by definition, for a lattice, any pair of points should have both the infimum and supremum. Clearly, the pair of points P and A, they do not have a least upper bound. Note that they do have an infimum, which is 0. Similarly, if you consider the pair of points q comma v, then they definitely have a supremum which is 1, as you can see on the screen. However, it can be shown that it does not have an infimum. The point clearly arises from the fact that if you consider the lower set of these 2 points, q, v, then it consists of p, a and 0, and we will not be able to find the largest of these lower points. Now, it brings us to discussing the lattice of fuzzy sets. Recall the usual ordering on the set of fuzzy sets, which is looking at them as functions. We assign the pointwise ordering between any pair of fuzzy sets. We have seen that if we consider f of x to be a set of all fuzzy sets defined on the domain x, and by 1 tilde we denote the function which takes the membership value 1 throughout x, and by 0 tilde the function whose membership value at every point of x is 0, we have seen that considering this set of fuzzy sets and the usual pointwise ordering and these two functions 0 tilde and 1 tilde, it is a bounded poset. However, we can go one step further and say that this actually becomes a bounded lattice. So the question immediately arises, if it were a lattice, given any pair of elements from this set of fuzzy sets, what would be the meet and what would be the join? Let us calculate this. Remember, we have that a1 less than or equal to a2 if and only if a1 of x is less than or equal to a2 of x for every x in x. Now, we want to find the supremum of a pair of elements. The supremum of a pair of elements means we are looking at a1 join. Just for the sake of symbolism, let me just put a circle so that we do not immediately confuse it with the max that we are thinking of. This is what we need to find. However, this is also a function again. That means this is an element of f of x, which means this has to be defined on every x. That means we are looking at supremum of a1x, a2x, and we know that these are elements coming from 0, 1 interval, and with the usual ordering, the supremum on this turns out to be the maximum for a pair of elements, or if it is a set of elements, it would be the supremum. Since we are considering a pair of fuzzy sets, a1x, a2x is a pair of elements coming from 0, 1 interval, and this turns out to be max of a1 of x, a2 of x. Thus, the supremum of any two elements in f of x turns out to be the max of the corresponding fuzzy sets. It can be shown similarly that the infimum of a pair of fuzzy sets is actually doing the pointwise minimum on the corresponding membership functions. Thus, min and max, the operations that we have seen on fuzzy sets, they turn out to be the lattice operations of meet and join on the set of fuzzy sets with respect to the pointwise ordering. Let us look at a special type of lattice called the complete lattice. A lattice is said to be complete if every subset S of L has both the supremum and the infimum. That means both the join S and meet S exist. Let us for a moment consider the unit interval 0, 1 with respect to the usual order. We already know it is bounded. It is bounded above by 1 and bounded below by 0. Also, it is a complete lattice. That means any subset of 0, 1 we take, it has both the supremum and the infimum. Please note the supremum and the infimum of a set S, a subset of 0, 1, need not belong to S itself. It has to belong to the larger subset, the superset of it. So as subsets of the 0, 1 interval, any subset of 0, 1 interval will have both its infimum and supremum. Thus, the 0, 1 interval with the usual order is not just a bounded poset, it is a bounded lattice. In fact, it is a bounded complete lattice. In fact, from the definition itself, it follows that every complete lattice is bounded. This can be immediately seen by taking S to be L itself, in which case the join of L and the meet of L will exist, and they will turn out to be the upper and the lower bounds of L. Look at this example. It is a disjoint union of two intervals 0, 0.4 where 0.4 is not included, and 0.6, 1 where 0.6 is not included. While this is bounded with respect to the usual order, it is not complete. Consider the interval 0.3, 0.4, perhaps even open interval 0.3, open 0.4. We see that infimum of this interval, open 0.3, 0.4, is 0.3, which definitely belongs to the set. However, the supremum of this interval does not exist. Thus, we might have a lattice which is bounded but not complete. However, every complete lattice is actually bounded. Let us wind up this lecture with this very important result. We have seen the set of fuzzy sets on X with respect to the usual pointwise ordering is a bounded poset, in fact a bounded lattice, where the lattice operations were given by the min and the max operations on the fuzzy sets. It can also be shown that it is in fact a complete lattice. A few noteworthy observations can be presented. We have seen that there are many interpretations of conjunction. However, min seems to hold its position. The proof of the above result is in fact inherited from the fact that 0-1 interval is a complete lattice. We have seen this a few slides back, that the 0-1 interval is in fact a complete lattice. The proof of the above result can be easily inherited from this fact. And what this shows is that the representation of fuzzy sets that we have come up with as a function from X with the codomain as 0-1, which is a complete lattice, is a useful and an appropriate one for us. In this lecture, we have seen lattices, which are a special type of poset. We have seen that the set of fuzzy sets can be given a latticeal structure. In fact, they can be made a complete lattice. And also the fact that min and max, these operations arise quite naturally in this setting. And the representation of fuzzy sets that we have chosen seems to be both useful and appropriate. What lies ahead? We have seen lattice from an order theoretic perspective. In the next lecture, we will see lattice from an algebraic perspective, and it is through that we will come up with an algebra on the set of fuzzy sets itself. So the next lecture, we will deal with one particular algebra on the set of fuzzy sets. Thank you for joining me in this lecture, and hope to meet you soon in the next lecture. Thank you.